Well, thanks a lot for the invitation. It's always a great pleasure to be here at CIRM. It's my third time since the beginning of 2022, and I look forward for the fourth time. Okay, I must confess, I'm thrilled and scared to speak in front of such a crowd of geometers about geometry. But let's see how it goes. So feel free to interrupt and teach me some geometry, because I'm a probabilist, as Hugo said, and I will try to show mainly pictures to get you some of inspiration of what we've been trying to do with Timothy, Thomas, and Bram, and still trying to do. And so it is designed to be a light talk, not technical, so please feel free to interrupt. All right, so random maps, hyperbolic surfaces. My goal is to show you a few tableaus, a few big pictures, trying to convince you that there is a parallel between the theory of random maps and the theory of hyperbolic surfaces, and that we can build bridges between those two theories. The first tableau is about results. So I will present a few results, first dealing with random maps, and to be specific, I will be dealing with random triangulations. I don't know why there is an S there. Forget about that. Okay, so you have a bunch of triangles. These are real triangles. I mean, sheets of papers that you cut with your scissors, triangles, and you glue them together along their edges with some random fashion. To be specific, you imagine that we do an orientable gluing, meaning that your paper is colored black on one side and white on the other one, and when you glue black with black and white with white. Huh? So to get an orientable gluing. If you do that, if you do this gluing construction on this pattern, you will get a sphere here. Well, it's kind of easy to see because those arrows are not crossing. But in general, if you do a random gluing of these, I don't know, 10 or 12 triangles, then you will get a much more complicated pattern. And the shape that you will get, the manifold that you will get out of this gluing, will not be planar, will not be a sphere. So I did it for real, the real experiment, you know. It's my hand there. And you can perform a few of these gluing, but the last two gluings that you have to perform is the green with the green and the red with the red. And from the picture, from the simulation, you should be convinced that you would get a Genius 2 surface, 2 holes. Okay, so if you have kids, you can very nice exercise. Okay, so what we will do is we will do that for very large n. So you have n triangles. N has to be even so that when you perform the gluing, there is an even number of sides to pair together. And we will denote by t dot n. The dot will mean that I'm not specifying the genus. It's totally random. Only the n is fixed. A uniform triangulation that you obtain after gluing n triangles. Okay? Then it turns out that when you do that, the genus of the surface that you will get is very close to be maximal. N/4 is the maximal genus you can get from gluing n triangles. It's a corollary of Euler's formula. And so typically the genus will be N/4 minus some log times a random variable, and it's just a Gaussian standard variable. So forget about that. Imagine just that the genus is close to be maximal.
That has the mean? That has the expected value of the genus? Or?
No, okay. If you want the real statement.
Sorry.
No, but okay, you want to do probability, yeah? As you. You know, I can do that, but then don't be scared. You take the genus, you subtract n/4, you divide by log n, then you've got convergence in law. Let's put a minus so that this guy is positive, towards a random normal standard variable. Okay, you prefer that? Convergence in law or in distribution as n goes to infinity. And you also have convergence of the expectation if you wish. if you prefer taking the expectation of this guy, so that this is a number now, this is a real number, and then if you subtract n over 4, tac, tac, you divide by log, then you should get also convergence towards something explicit. All right. Web? You're totally right. You're totally right. You are totally right. You are totally right. So let's put 1 here. Yes. That's still convergence in distribution for the random variable, which is 1. So it's also called convergence in probability. And as Thomas was saying, he's right. If you get the second order, you have the genius. You subtract n over 4. You subtract also log n. And now you have to renormalize by square root log n to get convergence in distribution towards, with a minus because this guy is negative, towards a random normal standard Gaussian.
What does it mean? It means like when n is very large?
Then first order is n over 4. Just remember that. The first order is n over 4. It's a random guy, this genius, but if you look at one specific sample, it will be n over 4 with very, very, very high probability when n is large. Yes?
You take n equals 20.
Yes.
You already vary.
Yes. Yes. Okay. So that's for the genius, but if you look at the geometry of the triangulation you will get, so you have a random triangulation, you can see that as a graph, and you can look at the geometry of this graph. And if you plot the geometry of this graph using Mathematica, you will get those guys here. I don't know if I have a pointer. Yes. Up? No, does not work. Anyway. So you see that this is a random geometry. Why? Because these are 3 different samples. And actually, you see very few vertices in the graph. These very few vertices, you've got first order log n. It's the same log n as this one. So you have log n vertices, but they have a very high degree. So the degree of those vertices is of order n. Not exactly n. It's a random thing in front of the n. But you see that you have many multiple edges and many loops in your graph. And hence, this graph has a very small diameter. You've got log n vertices, many edges between them, and the diameter of this graph is small, is of order 1. So there are many people who have contributed to this, and if you want one open problem, and if you're fed up with the talk right now, you can stop and think about this conjecture that we have with Thomas and Bram. We believe, so we have a model where we can prove this conjecture, which is not this model of triangulation. The diameter of this random triangulation should converge in distribution towards a random variable with support 2 or 3. What do I mean by that? I just mean that there exists a constant that is kind of explicit. It's about 0.3, blah, 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 blah. Some constant, so that the probability that the diameter of your random triangulation unconstrained genius is equal to 2. This converges, it's a probability, so it's a number, converges toward psi as n goes to infinity, and otherwise, the probability that the diameter is 3. Actually, I think if it's 1 minus psi here and psi here. Okay, so if you have gifted graduate students, hop, very nice exercise, homework. The diameter is itself random, but it converges in the large n limit towards some random variable whose support is 2 and 3. We have a more precise conjecture, and if you're interested, then come to me, or one of us will present tonight. I don't know. Okay, questions about that? Okay, so this diameter is 2 or 3, as I said. But if you look at the dual graph, what is the dual graph? We were gluing triangles. So let's look at the dual picture. The dual picture is we are gluing vertices with 3 legs. We are building trivalent graphs or trivalent map. And how do we build that? Well, it's called the configuration model. You build that. You start with your n triangles. In the dual form is this n tripods, and you glue the you pair the edge, the half edges, the legs uniformly at random. Okay. And now, if you look at this dual graph, it's a well-known result. Goes back to the 80s of Bolobash and Fernandez de la Vega. That actually the diameter of this graph is of order log n. And the closest, it's the smallest diameter at first order that you can get from a trivalent graph with n vertices. Okay, and more interestingly for what will come, if we take this dual graph, which is still a random graph, and we add a new layer of randomness, we will decorate each edge independently with an exponential random length. So, okay, you've got edges in your graph, loops, and so on. And on each guy, you put a number, 0.6, 0.4, whatever. And these are distributed according to this law, just the exponential law. So these are random, independent for each edge. So this gives you a metric graph, if you wish. And now you look at the statistics of all cycle length. What do I mean? Well, you have cycles in this graph. You see, you have loops. And sometimes you have 2 edges like that, a cycle of length 2 and cycle of length 3 and so on. And if this guy is decorated by 0.8 and this guy is 0.7 and 0.4, then you have one cycle of length 0.8 and here one cycle of length 1.1. Okay? So you look at the statistics of all these cycle lengths and you order them. You take the smallest one, then the second smallest, and so on and so on. Then this guy converges towards something random, which is called the Poisson point process, with this intensity, sinus, hyperbolic sinus over t. What does that mean? That means that if this is your cycle length, then you will see a few of those lengths here, and more of those guys. And the intensity of this guy is this intensity function, the hyperbolic sinus t over t. Okay? And it has been observed by very recently by Johnson and Loof, Dante Johnson and Baptiste Loof, that if you do the same thing, but you restrict also to the unicellular case, so to the case where after the gluing you've got one phase, which is some event of probability roughly 1 over n. So it's something that puts some constraint on the graph. Then you've got a statistics of cycle length which has this intensity now, cosh minus 1 over t. All right. So that was for maps with unconstrained genus. Now let's put a bit more topology inside the game and let's constrain the genus. Questions, maybe? Yes.
T over T.
Yep.
There's also a law like those one. This one of the incidences there are in the universe.
Wait for the end of my talk.
Oh, I'm sorry.
No. But you're a very gifted student. Okay, so now let's constrain the genus. So recently Thomas and Baptiste, they proved that the number of triangulation with n triangles and genus G grows like this. And in particular, look at the expression n to the 2G. So there are more and more triangulation with high genus. That's why if you sample a triangulation uniformly at random, you will, with very high probability, land on a triangulation with the maximal possible genus, roughly. So now what we will do is we will take the opposite. We will constrain the triangulation to have the minimal genus. G is equal to 0, the planar case, right? So this is a very unlikely event for T bullet n, something which is decaying like 1 over factorial, so it's very, very unlikely event, but still, we will do that. Let's first start with simulation. So I will show you a few simulations of random triangulations with a couple of thousand triangles glued in a uniform manner, condition of having the topology of the sphere, genus 0. And this is displayed in 3 dimension. So, sure.
Does it mean that every time it's not 0,
if you were to do that, since the event is 1 over factorial, by the reject algorithm, wow, you should wait a long time before seeing one guy. So I will present other ways to simulate. Very, very good question. So no. I'm not simulating with the reject algorithm. Of course not. Okay, so in 3 dimension, this is not an isometric embedding, but it is as close as possible to be an isometric embedding. So what you see is a good flavor of what the geometry really is. So this is the rocking horse. This one is another simulation. So you see that the geometry is really random. And that's the goat with an umbrella. You can see the umbrella, I guess. The mask of the executioner, also called the beheaded chicken. Period bleu and period rose. So these are simulations. So you see that the geometry at large scale is really varying as you simulate. And the big theorem that goes with those pictures is the theorem of Jean-François Le Gall, back to 2011. If you look at this triangulation as a graph, so you equip its vertex set with the graph distance, then the take-home message is that the order of magnitude of the diameter is n to the 1/4. And this is a random variable. That means that this, okay, I will not enter the details of the subtleties of the Gromov-Hausdorff convergence, but what it tells you is that if you fix 2 numbers, A and B, say, positive, and you look at what is the probability that the diameter of your triangulation with genus 0 and n triangles, the diameter is at the order n 1/4 belong to some interval AB, then this converges as n goes to infinity towards some function of A and B, which is the probability that the Brownian sphere has the diameter between A and B. Okay, so what is this guy? Just to scare you a little bit I'm scared with geometry, so let me scare you a bit with probability. So the guy on the right, this S delta is a random compact metric space. So it lives in the space of isometric classes of compact metric space, the Gromov-Hausdorff space. And it is some kind of continuous metric space because it has a Hausdorff dimension 4, really fractal, although it is almost surely homomorphic to the 2 sphere. So it's topologically a sphere, but metrically as dimension 4. Now you're scared. Now let me scare me. That was part 1 of tableau 1. Let's go to part 2. Random hyperbolic surfaces. Okay. Now I am scared. Let MGN be the moduli space of isometric classes of closed hyperbolic surfaces with genus G and n punctures. So I guess most of you know this space. And most of you study this space. You all know it's a nice space, but that we don't understand very well. And we understand much better the Teichmüller space TGN. And for those who don't know what we are dealing with, let's go down to earth and let's consider gluing of hyperbolic pairs of pens. So you have a hyperbolic pairs of pens factory, and if you specify 3 numbers A, B, C positive, there is a unique model of pent with 3 boundaries of length A, B, and C. Okay, that's a pair of pens. You know, when you look at numbers on your pair of pens, you've got two numbers, but here you've got three numbers, A, B, and C. And you go to your factory and you specify these three numbers, and they give you one hyperbolic pair of pens. If B is very small and no jealous, for any A, B, and C, the area of your genes, of your pair of pens, is the same. So that means that if B is very small, if you have a small belt here, then the leg will be very long. So let me show you an example. When B is small, you have a very long leg. And if C is large, then the leg is smaller because the area is constrained. Okay? So believe me, almost 0 and C. Okay? And here you've got a metric, which is the hyperbolic metric. Now you can glue those pairs of pens using the combinatorics of a trivalent graph. You can see on this picture. If you have some numbers, so a trivalent graph that you see, it's the dual of these pens. And you can, if they have the same, okay, I don't have a pointer, but maybe I do. Yes, I do. So this number is the same as this one. This number belt length is the same as this one, and so on and so forth. You can glue these pens according to this length. If they have the same length, you can do. But you also have a parameter here to decide to twist a little bit your pens before gluing them together. And after the gluing, what you get is a hyperbolic surface. And all hyperbolic surfaces can be obtained that way. Okay? So here you've got n is equal to 1. N is the number of cusps. Cusp is when one of these parameters is 0. So when of this parameter is 0, you have a leg of infinite length, but kind of small. Okay. So now we will want to sample one of these hyperbolic surfaces at random. So I need to specify a measure, a probability measure. And this is done, there are many ways to do that, but one convenient way is to use this coordinate system. So once you have your trivalent graph, you have for each of these blue circles here, you have a parameter which I call xe, which is the length here. And you have a parameter theta e, which is the amount of twist you need to turn before gluing. These are called the Fenchel-Nielsen coordinates. And once you have specified in gray the trivalent graph here, you have how many parameters? Well, it's a little counting, but you have 3g minus 3 synapses like that, right? And for each of these region, you have one parameter xe, which is positive, lives in R+, and the theta e, the twist, lives in R. So you can, for any of these choice of xe, theta e, get after gluing a hyperbolic surface. And so what you will do is you will consider just the infinite Lebesgue measure on all of these parameters. It's a way to say this is the Teichmüller space. But the problem is that there are many, many parameters that will correspond to the same hyperbolic surface. One obvious thing is that if you do a full turn, if you have your two pens and you do a full turn and you glue back, you get the same hyperbolic surface. So this parametrization like here is really over-parameterized. You are counting many, many, many times the same hyperbolic surface here. However, if you put the Lebesgue measure here, then Wolpert proved in the 80s that after taking the quotient, so identifying two coordinates here that lands on the same hyperbolic surface, you can pass to the quotient of the mapping class group, if you wish, and get a finite measure on the set of hyperbolic surfaces. So we have a natural measure that lives on the moduli space, which is called the Weil-Petersen measure. Okay. So if you're not familiar with that, think of this as kind of the Lebesgue measure on this space. And since it's a finite measure, you can normalize it to be a probability measure and sample a hyperbolic surface using this measure and get a random hyperbolic surface that we will be denoting by SGN, random hyperbolic surface sampled in this MGN using Weil-Petersen. Exactly as for triangulation, let's look first at the case when the genus is very, very large, and after we will look at the case when the genus is 0. So we will first look at the case when G is sent to infinity and n, the number of punctures, is 0. So no punctures like that, no legs with 0 boundary at the end. Then Mirzakhini proved 15 years ago that this random surface has a logarithmic diameter. The diameter is of order log, has spectral gap, positive Cheeger constant, and so on. So many similarities with the world of random graphs. Although the constants are not optimal in the sense that we still don't know, for example, for the diameter, whether this guy, SG0, if you look at its diameter and you divide by log G, whether this guy is random or not in the large G limit. We know it's between 1 and 40, let's say, with very high probability, but we don't know whether it concentrates or not. Okay? And with Bram, she proved that same thing as for graphs. If you look at the length of closed loops, so you have a very complicated surface. You know, this guy is, no, sorry, Hugo, genus 17. This guy looks like that, no? Not at all. No, it's much more complicated. You've got holes, but they are, you know, well, impossible to draw. So, but there are loops somewhere. And you look at the statistics of the length of all these loops, geodesic loops, because otherwise you've got many, many loops. And they prove that the statistics of these closed loops, if you order them from the smallest one to the largest one, converge towards a Poisson process with intensity that we already encountered, this cosh minus 1 over t. And there are many other works studying the geometry of those surfaces as the genus goes to infinity, in particular the works of Hugo, and very recently many works on the spectral graph. So that was for the large G limit. Now let's look at the genus 0 case. Well, in genus G0, we are completing a work with Timothy showing that the same thing as for maps, as for triangulation. If you look at S0n, genus 0, n punctures, then the order of magnitude of the diameter is n to the minus n to the 1/4. So if you renormalize the distances by this guy, then you've got convergence again towards this Brownian sphere. A few stars here, okay, no, not in the same sense as before, because this guy, so this is an instance of a random Weil-Peterson surface in genus 0 with many punctures, a couple of maybe hundreds. This is of infinite diameter, but because of the cusps. But if you cut a little bit the cusp, this goes back to finite diameter. And for those who know, yeah, just consider the Auer cycle neighborhood with length 1. You get rid of the rest. And after doing that, the diameter of the space you see is really n to the 1/4. And it converges towards the same object, the Brownian sphere. Okay. As you say, Peter, there are a few coincidences, right? Well, okay. Why few coincidences? Because we saw in the large G limit the same statistics. In the G0 limit, G0 n punctures, n goes to infinity, the same limit, the Brownian sphere, something fishy. That was the first tableau. Let's go to the second tableau. Now I will present you a few tools that we use in by Federica. A few tools that we use in random maps and that you guys use in hyperbolic surfaces, and show you striking similarities. So two tableaus, one dealing with the pinning process and one with tree bijection. So let's start with the first tableau, Tut, Mirzakhini, and the pinning process. Okay. Before I get to the second tableau, are there questions about the first tableau? No? Yep. Yes, yes, but you renormalize by n to the minus 1/4. So the holes, they have diameter, say constant diameter, but after you renormalize, they squash. Good question. Okay, so forget everything. Not everything, but just what happened in the last 20 minutes. And let's go back to triangulations. We will try to count triangulation in the genus 0 and triangles. Genus 0 and triangles. And the way to do that is actually to incorporate an additional parameter, this parameter P, which is the boundary length of such a triangulation. So we glue triangles, as you see here, but we don't have the topology of the sphere. We have the topology of the disk, except at these pinch points. And so we will count the number of gluing such triangles so that you have a boundary of length P with n triangles. Call this set T0 and P. Then the idea of TUT is very down to earth, very simple. If you want to enumerate this set, you take such a triangulation, you have a distinguished oriented edge here on the boundary, and let's see what happens if you remove this edge or if you explore what is on the other side of this edge. So what is on the other side of this edge might be you have two cases. Either you discover a triangle like that, or if you remove this edge, then this will split the map into two parts. There are these two cases, or let's forget about that. But if you discover a triangle, that means that in the remaining map here in white, you must have n-1 triangles because you just discovered one, and the perimeter has increased by 1. Otherwise, if you split the map in two, that means that the number of triangles here, n1, and the number of triangles here, n2, sum up to n-1, and the perimeters, they also have some constraints. They have to sum up after 2 to p. Okay, so you have a very simple plain recursion on this T0 and P using this recursion. And now, TUT, simple recursion, but to solve explicitly the recursion, this is not easy. But TUT managed to do that, and there is a lot of literature about solving those equations. But now, this is combinatorics. Now let's do probability. We will interpret this TUT's equation into a random growth or exploration process of a random triangulation. What do I mean? I'm saying exactly the same thing in probabilistic language. Imagine that I fix NP and that I sample a random triangulation with n triangles and boundary P. So what is inside here has to be thought of as random, these question marks. It's a random triangulation. I don't know it. It's random. And now I want to explore what is on the other side of this edge, of this root edge here. Then again, two cases. Either I discover a triangle and I have a random uniform triangulation here with the proper constraint. And this happens with probability, which is just the ratio of the numbers that we were computing. Okay? Otherwise, if I discover this edge that might separate the map into two parts, n1, n2, p1, p2, which are random numbers, and this splitting event happens with probability. This is exactly the same as TUT equation, but the glasses that I put are different. I see that as a random growth process, and I discover my random triangulation edge by edge after, sampling those two transition probabilities using those numbers. Why is that interesting? This is interesting because now we can do something that TUT did not do, is that we can choose where to put this arrow here, where to explore the map. Right? Because, okay, I wanted to explore this edge here, but I could have explored the edge here. So put in different words, I have different ways to choose the next edge to peel. In our language, we say different peeling algorithm. And this leads to different ways to explore the triangulation, hence different type of geometric information. So although the probability transitions are the same, I'm not exploring the triangulation in the same way. Okay? So It's exactly Todd's equation, but with many ways to implement the growth process. And this had very nice application in the realm of planar maps. For example, you can choose the edge to peel, the next edge to peel, according to different type of algorithm. And for one algorithm, you study the volume growth and recover this n to the 1/4 diameter. You can also use that to study the behavior of the simple random walk, something which I did with Itai Benjamini, with another algorithm, and yet with yet other algorithms, you can study percolation on those guys. So just the take-home message is that there are many ways to implement Todd's equation in probabilistic language to get different type of information on the random surface. Okay, now let's do the same for hyperbolic surface. We do the same, genus 0, n punctures, and we put another parameter L, which is the boundary length. So this is the analogous of this T0NP in the realm of hyperbolic surface. I consider the Weil-Petersson measure, I don't normalize, of all of this hyperbolic surface with genus 0, n punctures, and a boundary, single boundary of perimeter L. And I'm looking for the equivalent of Todd's equation here. This has been done by Mirzakhini, and the analogous of Todd's equation is based on this generalized max chain identity. She said that if you take one of these surfaces and you pick a point on the boundary L, here you pick a point and you throw an orthogonal geodesics, then unless if you are very unlucky, this happens with probability 0, this geodesic will either find its way out through this boundary or bounce on itself and will define for you a pair of pens. Okay? Once you have defined this pair of pens, this is the pair of pens that contains the smallest one that contains this hyperbolic geodesic, then this will split your surface into two new components with a new boundary L1, N1, N1 punctures, and new boundary L2, N2. Well, this is exactly the analogous of Todd's equation. This is discovering one triangle, and you split the map in two. We said that sometimes we were not splitting in two. Yes, this is the case when this L1 is actually 0, and N1 is 0. Or 1, I don't know, 1 punctures, let's say. When you have this up, you have 1 puncture, up, and your geodesic does something like that. Up, you have 1 puncture that you single out on the left, and you have not split the map, not the map, but the surface, into 2 parts, but only 1. Okay? Well, the same. This leads to a recursion on Weil-Petersson volumes. Again, the recursion is easy to see from this picture, but solving the equation, to my knowledge, is not done in full generality. But then you have the equivalent of Todd's equation, so let's implement the same thing as we did for planar maps. We want to develop the peeling process of Weil-Petersson surface. More precisely, exactly as for Todd's equation, we have many ways to pick the point on the boundary where to launch the geodesic. Many algorithms. And so we have many ways to explore the surface. Same recursion, but many ways to explore the surface. Okay, so we explore pair of pens after pair of pens by throwing geodesics, and the way we throw those geodesics, the starting point here, depends on the algorithm you pick. Regardless of the algorithm, the law of the tree that you see here, the tree decorated with this length, this is a random labeled tree, this law is independent of the algorithm you choose, and for example, we want to, so still work in progress, we want to understand the law of the tree that you would get, and actually those trees, they are not the usual type of random tree that we encounter. They have a diameter which is n to the 3/4, and so what you see here, the color is the length of the perimeter, and so the typical perimeter is n to the 1/2. So that means that if you take one of these Weil-Petersson surface and you explore and you look in the middle, what is the length of those blue belts? It's roughly square root of n. All right. Something fishy, right? Same thing in planar triangulation and Weid-Peters. Right. That's something that will help us for the third tableau. But let me interpret a little bit more this Mirzakhini's recursion. We saw that this in the Felschen-Nielsen coordinates, this mapping, so if you prescribe coordinates here where to glue and so on, and after gluing you get a hyperbolic surface, this is way over parameterized because many coordinates, many xi, theta I will lead to the same hyperbolic surface. So this arrow here is very surjective. But actually, you can see this Mirzakhini's recursion as imposing geometric constraint on the pen decomposition. So, in a way, this pen decomposition here, it is a pen decomposition of your surface, but it has the particularity that for each of these pens, if you throw the geodesic from this point, then the geodesic will stay in the pen. So it is a geometric condition that you impose on the pen decomposition that will actually single out for you a unique coordinate in this representation. So you can see Mirzakhini's recursion as a way, as a section. You start from a hyperbolic surface and you build a pen decomposition that has a particularity, which is the case that the pair of pens are compatible with the lengths that you have. Lengths of geodesics, whatever. And so, okay, this is a way to go back and to get unique coordinate for a given hyperbolic surface. Questions? You're lost? Good. If you're lost, let's go forward and move to the third tableau. You know, I said it is impressionistic. Third tableau, Penner, Schaeffer, and tree bijection. For those who know, I choose the foci. Comment on dit la foci in English? Oh, sorry? Okay. Yeah, but I choose the foci because the peeling process requires care. You have really to, you know, it takes some time, and the hammer, bam! So it's not a coincidence. So let's start with the case of maps. So to spare you a bit of technicalities, I will change a bit my model of maps, and instead of considering triangulations where I was gluing triangles, I will now consider quadrangulations where all the faces are quadrangles. I'm gluing quadrangles instead of triangles. All of what I'm saying can be adapted to the case of triangulation, but it's more technical. And actually, we will encode those objects. So again, genus 0 and n quadrangles. We will encode those objects via much simpler objects, which are labeled trees. And the labels on this tree will represent distances in the map. If you have never seen that, it's black magic. So let me do for you the black magic. You see here a tree, and you see labels, which are integer labels, and they start from 0 at the root, and they evolve along the branches roughly like a random walk. They can move by plus or minus 1 or 0 along each edge. This encodes a map, a quadrangulation. How to recover the quadrangulation? You first put an additional vertex outside, and now what you do is you do the contour of the tree, like that. You will do the contour. You're a little squirrel that goes around the tree. And you start here, and when you meet a vertex with label I, here I is 0, then you want to link it to the next corner in the contour, which has label I minus 1. Well, why not? So this 0 will be linked to the minus 1. This minus 1 will be linked to the minus 2. This minus 2 will be linked to the next minus 3. There are no minus 3, so you link it to this delta. Delta plays the role of the minus 3. Then you go on. This minus 1 will be linked to the next minus 2. And so on and so forth. Black magic. Really, as I said, it's black magic. Up, you do that until you get full turn. what you see in red is a quadrangulation. So erase the tree in your head, you will see this map, which is a quadrangulation. And that's a bijection provided you do the good routing, pointing, and so on. But I said that the labels, they are metric interpretation. Indeed, remember that this delta plays the role of the -3, and so let's shift all labels by 3 so that they become positive. If you shift all the labels by 3, this becomes 0, 1, 1, 1, 2, 2, 2, 2, and so on. And look at these labels. They are the distances in the map from this black dot. So the labels have a metric interpretation in the map as the distances from one point. Okay, now you've got a lot of techniques, but getting the scaling limits of such random trees is really the building blocks in the convergence, Legal's proof of the convergence of random triangulations or quadrangulation towards the Brownian sphere. Okay, shift. I claim that you guys, we've been playing with that for 20 years in the random map community, and I claim that you guys know this for random surface since the 80s. And it is Penner's decorated Teichmüller theory. Okay. Again, for concreteness, let me stick to the genus 0 case and punctures. So you have a hyperbolic surface here with 4 punctures, and we will triangulate those surfaces with vertices at the point at infinity, at the cusp. Forget that for 1 minute. I need just to introduce the lambda length coordinate in Penner's language. So you guys, when you see a disk, you think of the hyperbolic plane, right? So you see a disk, it is the hyperbolic plane. You have an ideal triangle here with 3 vertices. And if you pick 3 numbers, H0, H1, H2, which are the horocycles centered at those points, you can now consider what is this black length here, which are the lengths of this segment. Now there are not lines anymore. And there is this bijection between these 3 numbers, H1, H0, H2, and these 3 numbers, which are 3 lengths, which are the Penner's lambda length. So these are, think of the interior here as triangles where you cut a little bit the cusps of these triangles, of these ideal triangles. Okay, so now what you can do is, if you have an abstract triangulation here, genus 0, you see that's a triangulation of the sphere. Imagine that on each edge, I put a number, lambda. This can also be negative if the 2 horocycles they cross each other. So if I put numbers here, then I can imagine that in each of these faces, I take one of these truncated triangles with the proper lambda I, and that I will glue them according to the combinatorics of the triangulation. You see what I'm doing? Okay, so if I have lambda 1, lambda 2, lambda 3, and here lambda 1, lambda 4, lambda 5, if the lambda 1 is the same lambda 1, then I can consider the cut triangle here and the cut triangle here and glue them according to the same length in lambda 1. Okay? So if I do that, and if I glue, I will get a hyperbolic surface here with decoration on the cusps, which is the decoration that Penner called the decorated Teichmüller theory. Okay? Again, side remark, the Weil-Petersen measure that we considered before is nicely expressed in this coordinate system, but we've got the same problem here. We've got the same problem. We can think of this construction here as another combinatorial construction of hyperbolic surface. Remember, we had this gluing of pair of pens to get hyperbolic surface, and this gluing were way over parameterized. We have many ways to get the same hyperbolic surface. Here also, there are many, many ways, many triangulations, and many decoration of the length that will get to the same hyperbolic surface here. So it's way over parameterized. But as before, if we impose some geometric condition on the labeled triangulation here, we can specify uniquely the coordinate, meaning that I can, for you, for a given hyperbolic surface, find a unique triangulation and a unique labeling, so that after gluing, you get the hyperbolic surface. And this, you know, well, some of you know, it's the Bowditch Epstein-Penner-Voronoi construction. Let me present it for you. Again, in the genus 0 case with n punctures, how much time do I have? Good. So you have your hyperbolic surface, and you have one cusp which is distinguished, and you will consider you will imagine that you will float your hyperbolic surface starting from this vertex here. Okay, it's at infinity, but the water flows quickly and then invade your surface. And here, these are when the water comes from two different sides. These are the points from which you can launch two geodesics towards this point, one going that way and one going the other way around. Okay? And the guy in red here is called the cut locus, or the spine, which are exactly precisely those points where you can send different geodesics towards this distinguished point. And in the case of G0 n punctures, this is just a tree with vertices of degree at most 3, unless you're very unlucky. Now you can consider so this is your tree drawn on your surface. Now you consider the dual of this tree, meaning for each edge here, you will consider the loop, the geodesic loop, orthogonal, or let's say dual to this guy, and this will give for you triangle. And so you have a decomposition here as a gluing of triangles of your surface. Well, I claim, well, I'm not claiming Epstein, Bowditch, Penner claim that this is a unique representative of this surface. So you see the triangulation here, and the length that you see here, these are the lengths, you have to specify or a cycle here, but these are the lengths of those loops. Blah, 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 let me skip that. No. So, okay, you have decomposition in the hyperbolic triangles, but if you go back to the Euclidean case, this is just also a tree of triangles, Euclidean triangles. But as I said, you have to impose some geometric constraint. But the geometric constraint here is very simple. It's just a local constraint. Is that if you take two neighboring triangles, they have to satisfy the Voronoi condition. What is this Voronoi condition? So there are different ways to see that. Either this red part here has to be present, meaning that if you take all the mediatrices here, the bisectors, this part has to be present, or equivalently that the concentric, comment on appelle ça? Circumcircles, the circumcircles of this triangle should not include this point, and vice versa. So it's a local constraint. Okay, and so you have a tree decorated with labels which are this lambda length. Well, this is the same as for Schaeffer. Why? And let me finish with that. Well, actually, back to Schaeffer construction. In the Schaeffer construction, you remember you had a tree, the tree dotted lines, but actually the construction of the tree is almost the same in the discrete as for the Bowditch Epstein-Penner construction. Precisely, well, okay, no, let me skip that. It's a discrete cut locus. Clichy, right? Okay, let me finish with that. You know that at the entrance of the Greece Academy, it was written on the top, let no one but geometers enter here. But if you look very carefully on the picture, I found a small group of probabilists here, dubious probabilists, maybe Planche de Galton here, I don't know. They look dubious, but probably a few probabilists managed to sneak inside the academy. Thanks a lot for your attention.
Thank you very much. Questions? So I've been asked to pass the microphone to whoever is going to ask a question.
How do you generate the genus zero triangulations?
With Schaefer bijection. With Schaefer bijection. So I showed you, well, I told you that there is a bijection between these labeled trees and quadrangulation. There are similar bijection with triangulation, and simulating the labeled trees, this is much easier. So I'm generating the labeled trees, and then apply the Schaefer construction and get the triangulation. Or you could do that by the peeling process as well. If you have access to those numbers, this D0 NP.
Thanks for the nice talk. I was just curious, does it make sense to ask computational questions here?
To ask?
Computational questions, for example, given a triangulation, compute the genus in like polynomial time, or how it's the hardness like?
After the gluing?
Yeah.
You mean you are given combinatorially the gluing?
Yeah.
Well, this is very easy because you represent that as a system of permutation, and then you just have the product of two permutations to perform and to cycle decomposition. So it's very easy. Yeah.
I see. Are there any other questions computationally which have been studied? Could you think of? I mean, from a CS hat, I'm wondering. Yeah. Maybe offline. Yeah. No worries. Sure.
I don't know.
Thank you.
In the pair of points decomposition, you said that you have a single point in the Teichmüller space that is
with the proper constraint.
Yeah, and if I give you any representation as a point in the Teichmüller place, do you have any idea how to compute this unique representation?
I would do.
Okay.
No, this is complicated because if you have. No, it's complicated. No, you have to follow. Okay. Imagine you have your pair of pants up, and now that's in your Teichmüller space. You represent like that, but now you throw this geodesic orthogonal to that. If it goes through that, you have to explore the geodesic until the geodesic bounces on itself.
Okay, I see.
A nightmare for me.
And do you have any control on the quality of the unique representation, like the length of the... Is it not too far from Beer's parameters? Or?
Oh, no, I think this will be quite far, but we expect to get kind of results like the one with this picture. With this picture here, where we want to understand typically the perimeters that you get inside those trees. What are those perimeters? I'm not sure they will be optimal. I'm pretty sure they won't be optimal. But as a first step, we want to understand that.
And yeah, my question was maybe 2 slides, just a slide before the hammer.
The slide before the hammer.
The one hammer.
The one hammer. This is the slide. Yep.
No.
Yep. Yep.
So this leads to these Frenkel-Nielsen parameters that kind of sorts out an element.
Yep.
Like in the fundamental domain for MGN.
Yes.
So a question to the organizers, are there also office hours? Because I would like to learn this, but not in the lecture here. Is it
Yeah, in the Calanque.
The schedule is on purpose. Those 4 hours are not just to digest lunch.
I see.
It's not complicated. What I'm saying here is that you have many pens decomposition.
There is a way of sorting out.
Yes,
yeah.
and
So I would like to learn more about
Sure.
this in one of these office
With
hours.
great pleasure. I might be wrong, but would be happy to know. Well, Bram said yes. He is my geometry.
All right, hi. So we saw some fishy things today. I mean, do you have any conjecture at all, or any idea
but
why?
in the paper of Hugo and Gouth and Parlier, they say, there is also striking similarities. I'm not even not able to formulate a conjecture. But for example, what I would like to get is you give me, I would like to I don't know, I don't understand very well the Weil-Petersen measure, to be honest with you. So I would like to get a combinatorial model of maps so that after taking some scaling limit, this will converge to the Weil-Petersen model. For example, this I would be just to understand geometrically what is going on. So I would like a discrete model, geometric model, not something that counts VP volumes. I want really something geometric that after taking some scaling limit, you will get Weil-Petersen. So in the genus 0, when you have many, many punctures, well, it's the same as taking a triangulation. That's the result we have with TIM. In the large G limit, there are these fishy coincidences. I don't know how to formulate a conjecture.
All right, thanks.
Okay, so thanks very much. Let's thank Nicolas again.